Hi, I'm going to present on the power of system call traces, predicting the software energy consumption impact of changes. Basically, we are in this work we are trying to relate the system call traces of Android applications with the energy consumption profile, which is changed when you perform some code changes or commits. So in this work, we have proposed a simplified method of basically giving an indication of the change in energy consumption, and the central contribution of this work is the rule of thumb, which is quite simple to use by uh, developers in order to indicate that change. So we can imagine a scenario where we have a developer who just made a commit, but he's just thinking, how does this commit affects his application's energy profile. The thing is that most of the developers are unaware of the energy profile of their applications, because they have to, in order to estimate the energy, they have to rely on expensive instrumentation. So in this work we try to relate system call invocation counts to the app energy consumption profiles of the Android applications, in order to give an indication to the developers to have an indication of the energy profile change. So why do the basic question is, why do we care about the energy consumption of our applications? They are basically battery life, because battery life is quite important to the consumers. Also, if the developers are aware of the energy impact of the code changes of they make to the energy profile of their applications, they can optimize their applications to to have lesser energy impacts, hence also reducing the carbon emissions, because ultimately you have to produce energy for the phones to run. So they are you primarily produced from the unconventional sources, which lead to carbon emissions, hence the need for this work. So the research statement is, how can developers identify change in power usage profile of their applications without use of special instrumentation? So in order to answer this question, we start from basic description about system calls. System calls are basically the interface sitting between the kernel OS and the applications. The system calls are basically give the allocate the resources demanded by the applications from the kernel, and they pass off as an interface where the applications demand the resources. They call the particular system call. For example, to read particular bytes in a file, you'll call read system call, which will then get to the kernel and get those bytes and then return that data to the application. So in Android it is quite easy. There's a application called Strace, which helps to basically this is a screenshot of the Strace, where you have a browser and you have the corresponding output of the Strace. As we can see, there are system call profiles like epoll, wait, and clock get time, and fulex and write. So the previous works in this area have been by Dr. Ibram Hindoo on green mining, which is basically a procedural approach of how to relate the factors behind the energy consumption of software. Basically use the software matrix to find those the processes behind the energy consumption in a procedural way. And this work is quite related to the earlier work by Pathak et al., where they model the energy consumption of mobile applications by constructing finite state machines of system calls and the states of the components of devices they use. But it gets quite complex, and it's quite difficult for the general developers to emulate that work. So this works uses quite simpler way of using the system calls by using the counts of system call invocation rather than using those complex FSMs. So in order to find the usefulness of the system calls in that prediction, um, we follow this methodology of we choose open source applications, then we built APKs for the each commit because we want to see the effect of commits on the energy consumption. Then we design test suits because we need to find the energy consumption data and the test cases where the how the commit makes a difference to the energy profile. And then we run those test suits on the green miner, which is basically an internal infrastructure to get the energy consumption data, and then we get the results and analysis. So we consider two applications, calculator and Firefox. We had 101 commit version for calculator and 156 commit version for the Firefox. So we choose one test case each for calculator and Firefox. For the calculator, it was basically simulating unit conversion test and GST calculation for a duration of 125 seconds. For the Firefox, it was basically a simulating reading a Wikipedia page for a duration of 5 minutes. So these are screenshots for the calculator application. Then we run these test suits on the green miner. Green miner basically our internal test bed, which consists of 4 Galaxy Nexus phones, which are controlled by Raspberry Pis. Because the energy consumption data for each of we can trust on energy consumption measurements for only one run. We have to run it multiple times because there are quite a lot of variation depending upon a lot of factors. The energy consumption can vary for a specific version or for a specific test case as well. So we do 10 runs per version per commit version, and then get the mean values for that energy consumption data. Similarly, we run 10 runs per version for the system call trace as well to see the stability there. And then we had a total 400 hours to run these tests. So this is a screenshot of the green miner. This is a Galaxy Nexus phone, and this is a Raspberry Pi which is used to control that phone. So we saw the system call variation to see whether they are really stable or they are as unstable as the energy consumption. We found that they are not that stable, but these plots show the variance of the system calls for the 10 test runs for each version. So these are basically the red lines are showing joining the averages of those 10 runs per system call values. So we saw that they are not quite stable for the Firefox application particularly, because there the average variation was more than 5% per system call, whereas for the calculator mostly the system calls were quite stable. Most of them were less than 3%, had less than 3% variation on average, but some did had higher variation. This plot shows the energy consumption for the calculator application we selected for the 101 versions. So the plots show the basically the variation in particular version, and the red line is basically a trend across those versions. There were some error commits which was because of the bugs in the application, which led to the crashing of the application. So we had quite lower power values for them. There was not much variation in the power in calculator application. Similarly for the Firefox as well, we did have some variation but not as much, and there was a particular refactoring bug which led to higher energy consumption across 3 versions, um, and there wasn't a particular trend as here as well. So in order to find the relation between system calls and the energy consumption, we built linear models between the energy calls and individual system call counts, which we averaged. So we found that for the calculator application, the correlations and the R-square values were quite good, uh, but not for the Firefox. We had quite low correlation and R-square values. So because this wasn't quite useful, so we thought about using logistic regression to classify the versions into high energy and low energy commits with respect to the mean energy of all commits. Basically, we classify them into high and low energy commits with respect to the mean value of all the commits. So we had this initial data in the table in the upper table. We had the initial data, and then we transform it into low and high power values, and as well as we use the individual system call counts and take the average of the system call counts and then subtract them. As you can see, from 4073 we had 118 for the cache flush. So this way we get the features and the to make the logistic regression models. And then we made some models where all the system calls that were in that model were statistically significant. So we had in the calculator application, we had models which gave us an accuracy of 75% to 87.7%, whereas for the Firefox we had an accuracy of 68 to 80%. But this isn't quite useful. So considering the scenario of the developer, a developer would think whether a particular commit affected the energy profile of his application or not. So in order to evaluate this, we propose a rule of thumb which basically states that the energy profile changes significantly when the system call profile changes significantly. So whether the based on whether your whether your system call profile changed, you say the energy profile changed or not. So how to use it? This flowchart gives you an idea of that. So we had initial system call data, and then we perform a commit and we get the system call data 2. Then we perform the t-test, which is basically in order to differentiate whether the call profile has changed or not, and then it gives us whether it has changed or not, and then we can say whether energy has changed or not. This method is quite practical and simpler because it doesn't involve any special instrumentation like green minus, which we had to use. It's also quite simple to use, and it's quite easy and simple, and it's quite time-saving method to estimate the energy profile. So in order to find the usefulness of this approach, we use three statistics. Precision for high precision would tell us whether the cases where the energy profile change indicated by the rule of thumb were very true. A high recall will indicate that our rule of thumb was able to point almost all the cases where the energy profile changed. High specificity would be able to point out almost all the cases where energy profile did not change. So why is specificity involved, and why is it important? It's because very few commits are there which lead to energy change, significant energy change in the application's energy consumption. For example, in case of calculator, we had only 11% such cases. In case of Firefox, we had only 6% such cases. So high specificity means that because high specificity only considers those cases where the energy consumption hasn't changed significantly, it means that it would consider majority of the those cases, because in most of the cases there is no change in energy. So high specificity would help us. High specificity would mean quite high accuracy for our rule of thumb. So this is how our rule of thumb performed on the data we had. The precision and recall values were not that good in case of Firefox, but were quite good in case of calculator application. But the specificity values were quite good in both the cases, and you can also see how all the three matrix performed quite good on a rule of thumb when compared to the random guess values. So our method is quite rule of thumb is quite practical way of finding out the energy consumption change. And even if somebody doesn't want to use t-test, for example, consider a developer who just runs the 10 traces for his application before commit and application after commit, and he can just simply eyeball the say the system calls which he suspects have changed in the because of the commit. So, and he can if that has changed, he can think that his energy consumption has changed as well. So in conclusion, most of the system calls are mildly correlated to the energy consumption, and logistic regression models are able to classify high energy and low energy commits with quite high accuracy. A rule of thumb has quite high specificity, as majority of commits don't produce any energy changes. It's quite highly accurate in predicting the energy profile change, and because the rule of thumb is very simple and time convenient, so it can help save effort and expenses for the costly instrumentation like Green Miner, because most of the developers won't have the instrumentation like Green Miner to predict energy changes. Hence, a rule of thumb is would help them is quite highly accurate in predicting the energy profile changes. Thank you. And this is our future work, where we are building a tool to using this rule of thumb to predict the energy consumption change, and which would indicate the system call which have changed significantly, and the able to point out the code which is suspected to have induced that change. Thank you.